So, hello everyone. So, welcome to the second last or week 11th interaction session on the course on robotics basics and selected advanced concepts. My name is Soumya. I am your TA for this course, and I am a PhD student associated with IIT Gandhinagar. I work in the field of robotics. Okay. So, I think we are switching gears now. We are moving to wheel mobile robots. Okay. Before this, we saw control mainly. Like before that, we had kinematics, dynamics. Then last two classes, we were focusing on control. Earlier, it was linear control, and last time we saw non-linear control, and then we saw that how things take turn when we are doing non-linear control. If the system is just hold on. Okay, so your system is not linear, it is non-linear, and there are many things that cannot be taken care of by linearizing the system. So we also go for non-linear controllers, right? So we are doing all of this. Okay, so this time we are going to see wheeled mobile robots. We are going to see how do we model wheeled mobile robots, and then what are the kinematics and dynamics for the mobile robots or just wheeled mobile robots. So mobile robots can be of many kinds. So you might know the legged ones, which are very famous, or in legged, let's say you have many robots. It can be varying based on number of legs. Okay, and then apart from this, I think you know this thing. You might have read this wheel mobile robots on uneven terrain. Okay, and then you might have seen the kinematics and dynamics of these mobile robots on uneven terrain. So this lecture basically deals with the same thing. Just before I start everything, I want to show a video. So not many people have joined, but still I would show the video so that it is available on record for you to watch whenever you're there. Okay. So just let me change the recording sequence. It has to be window capture, and then it has to be Microsoft Edge. Okay. I think, yeah, I have to come here. And then I have to change it for you as well. So where is the meet tab? Okay, I would present something else, and then I'll have entire screen probably for now. Then I'll share. Okay, so I think it is visible now. So we can see this. If we see this video, you can see there is a mechanism wheel here. Just hold on, let this ad pass here. Do you see that? So these mechanism wheels actually help you in moving laterally. So there are omni wheels, there are mechanism wheels, all of them. So just let me share this video. It's a nice video and it can be used as a kit if you want to develop something. Okay, please see this. Again, this is an example of mechanism wheel, and you can see the lateral drift. this is an ultrasonic sensor here, and this is the camera, right? So you'll see how it also follows the lines later. Some ultrasonic because it is like that is something you and it follows the cat, follows the ball, also follows the path. Based on hand gesture recognition, it does whatever it is programmed for following the person. Okay, so this is an enabler kit that you can use. Okay. Apart from this, there are many robots available with different types of wheels. I think you can have a look yourself on all of these, related to all of these. Okay. Okay. So I will switch the window, and it's gonna be wireless display here. And for you guys, I need to move to meet, then I need to present. I'm not able to hide it. Okay, to present something else. I'll go for window, and in window, okay, this wireless display. Okay, I hope the screen is visible now. uh, just let me go back to my edge. Yeah, I think everything is in place. Okay, so we are going to start with wheel mobile robots. So these are usually called WMRs. Okay, so this is one of the most important topics in robotics because most real world robots that you see, whether in industries, warehouses, or even self driving cars, are wheeled robots, right? So we'll go step by step, starting from basic definition, then types of wheels, then kinematics, dynamics, and finally we'll look at uneven terrain modeling. So I want to you all to focus also on the intuition apart from the equations. Okay. So what is WMR? So a wheel mobile robot is basically a robot that moves on a surface using wheels that are in contact with the ground. So unlike manipulators where the base is fixed, here the base itself is moving. Okay, and then you might have a mobile robot which moves and have a manipulator on top of it which manipulates the environment. But the thing is not very simple now because instead of this fixed base, it is fixed on the mobile robot. But it is fixed in the local frame, but it is not fixed in the global frame. If you're seeing from here, this is also moving, this is also moving. So it's a bit difficult to plan, right? Okay, so examples include automatic guided vehicles in factories, AGVs, Mars rovers, or if there are some delivery robots, you might have seen all of them coming up. So here we have Science City in Gujarat, and we have mobile robots in the shape of an humanoid delivering various food items, samosa, coffee, and everything. Okay, then if you see look at the factories or the warehouses, there also you have robots which does the same repetitive task, so it basically avoids all the obstacles. Or if you have seen a forklift, it just goes there, attaches, takes all the things that are to be transported on it, and once that is loaded, it moves to the other place and delivers it there, right? So all of these are examples of AMRs, autonomous mobile robots. Okay. Then there are autonomous cars, so you might have heard about Tesla ones. So why do we prefer wheels? Because wheels are efficient, okay? They are fast and they are simple to control. So when you read about legged robotics, you might read there is something called gates, according to which you have to design how the legs are moving with respect to time, and based on that you'll be able to see if the robot is moving forward. Okay. Okay, so these wheel robots just have one disadvantage, that they do not perform well on rough terrains. That is where legged robots are better. So let's say if you have such terrain, a legged robot keeping its leg here and then here, having discontinuous motion, is better than a wheeled robot moving on it, right? Because it might topple off. You have the constraint to always stay on the ground, you cannot lift it. Okay, so now let's understand the type of wheels. So one is the conventional wheel, right? And this is something that you see in cars. It rotates about its axis and can be steered. Okay. The second one is omnidirectional wheels. This is very interesting. It has small rollers on the boundary. These rollers allow motion sideways. So a normal wheel cannot move sideways. Your car cannot move in this direction, but Omni wheel can. Okay. And the third is spherical or ball wheel. Okay. This is like a ball. It can rotate in all the directions, but it is mechanically complex. Okay. So now I want you to remember one very important idea. All the conventional wheels which cannot move laterally are non-holonomic wheels, and omni wheels have non-holonomic, and omni wheels have more freedom, they are holonomic. Okay, so we'll now understand what non-holonomic means, but before that we'll derive something and then we'll come to it. Okay, so yeah, you might have already understood this robots part. Okay, I think we can move with single leg kinematics. Yeah. So let's consider the state variables. There is a mobile robot, it can move in X direction, it can move in Y direction, and then it can orient itself. Let's denote it by phi. Okay. So what are the state variables? X, Y, and phi. Where XY is the position and phi is the steering angle. All right. So if we want to roll without slip constraint, then what would happen? We get, I'm not going into this derivation, but you might have seen tan phi is equal to y dot upon x dot. That is what is coming from here. So if we try to equate the components, it would be x dot sine phi minus y dot cos pi is equal to 0. Okay. So the velocity of the wheel must be along wheel, must lie along the wheel direction. So what is the direction vector? It is cos phi comma sine phi. Right. And what is the perpendicular direction to the wheel? It is minus sine phi comma cos phi. And what is the constraint that we have? It is v dot n is equal to 0. That means x dot comma y dot minus sine phi cos phi should be equal to 0. So from here what do we get? X dot sine phi minus y dot cos phi is equal to 0. Okay. So if there is a non-holonomic constraint, that means we cannot integrate to get position constraint. We can only have velocity constraint. Yeah. So at 0, 0, at the origin, can the wheel have any orientation? Yes, there are infinite possibilities. So constraint cannot reduce degree of freedom. Okay. So what is our final kinematic model that we have obtained from here? Let's write it as x dot, y dot, phi dot is equal to cos phi sin phi 0 plus 0, 0, 1 and let's have omega here, right? We have written phi dot is equal to omega, where v is the forward velocity and phi is the steering angle. Right. So let's talk about the constraints on rear wheel and front wheel. X dot sine phi, let's assume it to be psi now because phi we have already taken, minus y dot cos psi is equal to 0. And for the front wheel, it is x dot sine psi plus phi minus y dot cos psi plus phi minus L psi dot cos phi is equal to 0. Okay. The derivation idea here is both wheels must have velocity along their direction and there is instantaneous center of rotation on the body of wire robot. So you might have seen this kind of diagram. So from here, the final kinematics that we have here are x dot, y dot, psi dot and theta, and phi dot. Is equal to cos psi into cos phi Sin psi into cos phi sin pi by L and 0 into Vf plus 0, 0, 0, 1 omega, right? So the motion is basically rotation about instantaneous center C. Okay. Okay. So when we talk about tricycle and car, let's talk about tricycle first. So it has a one driven wheel, one steering wheel, and other wheel is just passive. Okay. So it must have single instantaneous center of rotation, right? Okay. So in tricycle, we have single instantaneous center of rotation C. Okay. If we talk about car like robot, are you aware of Ackerman's steering? So how do we find out the condition for it? Cot phi dot minus cot phi naught is equal to d by L. This prevents slip. Okay. Okay. Now let's talk about omni wheel robots. If we decompose the velocity, it can be written as r theta dot plus sigma cos alpha sigma sine alpha. So for alpha is equal to 90 degrees, we have r theta dot comma sigma. So three wheel omni robot theta dot is r dot x dot y dot psi dot. Okay. So key point here this is for three wheel omni robot, and the key point here is that it is fully controllable and there is no steering needed. Okay. Apart from this, you might have also seen in the lecture slip modeling, right? And what do we see here? If it is a case of ideal rolling, V is equal to R omega. Okay. But slip definition, lambda is equal to theta dot minus omega star upon y, right? Now if this lambda is equal to 0, which means that theta dot would be equal to omega star, it would be a case of pure rolling. If lambda is equal to 1, which means theta dot minus omega star would be equal to y, it is the matter of spinning. If lambda is equal to minus 1, it's skidding. Okay. So your tractive force is basically Ft is equal to mu a lambda into normal force. So peak friction exists. Beyond peak, it is unstable. Okay. Now, let's talk about dynamics. So your equations of platform basically involve these terms, right? And for wheel, torque is I theta double dot plus Ft into R. So without modeling the slip, control fails. Okay. And if we talk about control, we have already seen PID control last to last time, right? So your force can be written as Kv into xd dot minus x dot plus Kp into xd minus x plus Ki into xd minus x. Okay. If we go for model based control, it is torque is alpha tau dash plus beta tau. We saw this when we were studying computer torque control. Okay. So PID gives poor performance usually, and we have also seen in the lecture model based is better but slip sensitive. Okay. Now let's talk about uneven terrain. Okay. So the key problem here is there are two wheels, they have different contact points which leads to slip. Solution, we can have variable axle length, right? We can have torus shaped wheels. Okay. So let's go about surface modeling. X, Y, Z is function of u comma v. So in geometry, there are tangent vectors. And what would they be? They would be Fu and Fv, right? And if we want to find out normal to the surface, it's gonna be N is equal to Fu cross Fv mod of cross product. Okay. So in contact kinematics, we have 5 degrees of freedom contact: U1, V1, V2, U1, V1, U2, V2 and psi. Contact is non-holonomic and dynamic. Okay. So WMRs are governed by non-holonomic constraints. Wheel type basically defines the mobility, and slip is unavoidable, must be modeled. If there is a flat terrain, it is simpler, it is 3 degrees of motion. But if it is an uneven terrain, it is complex, and we might need to go up to 6 degrees of freedom to get the results correct. Okay. Okay, apart from this, what is left? Let me check. Okay, I think we are done with this. We can go with the questions now. Not going to into derivation, that is already well covered in the lecture. Okay. So, the first question is, a wheel rolling without slip on a plane can have motion only along the tangent to the path, can have motion perpendicular to the path, is described with 3 generalized coordinates, but contains only 2 degrees of freedom in velocities. Now this is a very important foundational question from WMR kinematics. Let's go step by step. So we model a wheel on a plane with q as a function of x, y and phi, right? Where these are the positions and this is the orientation. Okay. So there are 3 generalized coordinates, right? In non-slip condition, which is mostly important, it's x dot sine phi minus y dot cos phi is equal to 0. This means velocity perpendicular to wheel is 0. Okay. So motion is only along the wheel direction, which is tangent. Okay. So configuration degree of freedom is 3, constraint is 1, which is non-holonomic, and velocity degree of freedom is 2, which is basically an x dot and y dot or not in z dot. So let's talk about the options. The first option is it can have motion only along the tangent to the path. It is true because no lateral slip is allowed. Okay, no lateral slip is allowed, and also the velocity must align with wheel direction. Okay, this is exactly what the constraint enforces, and this is correct. Let's talk about the fourth option first. It is described with 3 generalized coordinates but contains only 2 degree of freedom in velocities. True, because there are 3 variables x, y and phi. One constraint is there which reduces the velocity freedom. So it is 3 minus 1, which is 2 velocity degrees of freedom. Okay, so this is also correct. The other option that we have is it can have motion perpendicular to the path. This is false because this is exactly what is forbidden. That would mean slipping sideways, right? It violates non-holonomic constraint. So this is wrong. The third option is it is described with 3 generalized coordinates. This is incomplete, hence considered wrong. Yes, it has 3 coordinates, but the question is about motion behavior. It ignores the constraints, right? So it is not a complete description, so we are crossing it out. So whenever you see rolling without slip, that means there is no sideways motion, only a tangent motion. Non-holonomic constraint is there, and degree of freedom reduces in velocity and not configuration. So wheel can point anywhere in 3 degree of freedom but can only move forward or backward. It just has 2 velocity degree of freedom. Alright. So first and fourth are the correct options. Okay. Let's move to second question. A wheel on a flat surface can only move if there is friction at the wheel ground contact point, if there is deformation at wheel ground contact point, if attractive force is developed at the wheel ground contact point, if the wheel and ground are rigid. Okay, so this question is basically testing your physical understanding of the motion generation and not just kinematics. Just hold on. Okay. Okay, Devditya, if you would have any question, please feel free to ask. I'm carrying on with the question and answers. Okay. So, so if a wheel on a flat surface can move only if there is friction at the wheel point contact, all of these are the options here. So, how does a wheel actually move forward? Motor applies the torque, right? Then the wheel tries to rotate, but rotation is not enough to move forward. Motion happens only when the ground pushes the wheel forward. So we need tractive force, which is Ft. And this is equal to mu into normal. Mu is the friction coefficient and is the normal force. Without friction, there is no motion. So either the wheel or ground must deform to generate tractive force. Okay. Now the first option is if there is friction at the wheel ground contact point. This is true because wheel provides the force needed for motion. Without friction, wheel just spins. Okay. Second option is If there is deformation at the wheel ground contact point, this is true because real wheels are not perfectly rigid. Contact is not a point, it's an area, and deformation enables force transmission. Okay, so this is correct. Let's talk about the option C. If a tractive force is developed at the wheel ground contact point, this is true. This is the actual cause of motion. Friction plus deformation actually generates the tractive force. So this is also correct. Option 4 is if the wheel and ground are rigid, false, right? Because if both of them are perfectly rigid, contact is a single point. Yeah. So there would be no deformation, there would be no traction generated, and the result would be that the wheel cannot move effectively. So there is no effective real force transmission. So whenever you see wheel motion or locomotion, think torque alone cannot generate motion. It needs friction, it needs tractive force, and in real systems, the deformation is essential. So a wheel moves not because it rotates, but because the ground pushes it forward. All right. Let's move to the next question. The motion of bicycle the motion of bicycle moving on a flat ground can be described by 4 generalized coordinates and no constraints. Can be described by 4 generalized coordinates, but there are 2 constraints in each wheel. And then can be described by 4 generalized coordinates, but there are non-holonomic 2 constraints in the 2 wheels, and can be thought of as a rotation about the instantaneous center. So for a bicycle model, we have Q is X, Y, psi and phi, where this XY is the position, psi is the heading, and phi is the steering angle. Okay, so we have 4 generalized coordinates, right? Second thing, each wheel has no slip constraint. So for rear wheel, it is x dot sine psi minus y dot cos psi is equal to 0. And for front wheel constraint, we have x dot sine psi plus phi minus y dot cos psi plus phi minus L psi dot cos phi is equal to 0. So in total there are 2 constraints, 1 per wheel. Okay, and both are non-holonomic. So the key insight here is there are 4 coordinates, there are 2 constraints, and they reduce the velocity freedom. So there is a very important concept for instantaneous center of rotation, ICR. At any instant, the robot moves as if it is rotating about a point C. Both wheel velocities direction intersect at this point. That point is the instantaneous rotation. Okay, if it is moving in this direction, then there must be an instantaneous center of rotation about which it is rotating. So the third option here is can be described by 4 generalized coordinates, but there are non-holonomic 2 constraints at the 2 wheels. This is correct, right? Because there are 4 variables x, y, psi and phi, and there are 2 constraints, 1 per wheel, and they're non-holonomic because they are velocity constraints. Okay. The other option is, fourth option is, can be thought of as a rotation about the instantaneous center. True. Motion at any instant is same it can be said that it is same as or happens due to rotation about instantaneous center of rotation. This is very fundamental to vehicle kinematics. Okay, so this is also correct. Okay, let's talk about the first option. Can be described by four generalized coordinates and no constraints. That is wrong. Completely ignores no slip condition. Without constraints, unrealistic model would be there. Okay. And the second option is can be described by four generalized coordinates, but there are two constraints in each wheel. No, each wheel gives only one constraint. There, that is no lateral motion. So total two constraints and not four. So this is also wrong. Okay. So whenever you see bicycle model, immediately remember there are four states x, y, psi and phi. There are two constraints, one per wheel. Motion is basically rotation about instantaneous center of rotation. So each wheel kills sideways motion. Intersection of directions actually give you instantaneous center of rotation. All right. Let's move to the fourth question. Just hold on. Okay, in the fourth question, we have in a three-wheeled tricycle with front wheels steered and moving without slip. The speeds of the two rear wheels can be arbitrary. Only one of the rear wheels can be driven. The speed of the two rear wheels must be such that there is single instantaneous center, and the speeds of the two rear wheels must be such that there are two instantaneous centers. Okay, so we need to understand the system. So it is a three-wheel system, right? And then it is a tricycle. So front wheel is steered and the rear wheels are not steered, right? So motion must satisfy no slip condition at all wheels. So for pure rolling or no slip, all wheels must rotate about one common point, which is instantaneous center of rotation. If not, the wheels will slip. Okay. For rear wheels, their rear wheels are in fixed orientation. You cannot steer them. So that their velocities must align such that both are consistent with the same instantaneous center of rotation. Right. So the option 2 here is only one of the rear wheels can be driven. This is true. If both rear wheels are independently driven, they may try to enforce different speeds. This can violate ICR condition. So one wheel drives, other adjusts free wheel. It is basically a free wheel or a differential type of robot. Okay. In option 3, we have the speed of the two rear wheels must be such that there is a single instantaneous center. True. This is the core condition for no slip. All wheels must satisfy same ICR. So this is correct. In the first option, we have the speed of the two rear wheels can be arbitrary. False. If the speeds are arbitrary, you won't have a common ICR and it leads to slip, violates the rolling constraint. So it is wrong. The fourth option is the speed of the two rear wheels must be such that there are two instantaneous centers. This is also false. Physically impossible for rigid body motion. A rigid body can have only one instantaneous center. Okay. So this is incorrect. So whenever you see this no slip plus multiple wheels, you have to know that single instantaneous center of rotation must exist. There cannot be arbitrary wheel speeds and the speed must be coordinated. So all wheels must agree on one center of rotation, otherwise they fight each other and slip. Okay. Let's move to the fifth question. The Ackerman steering in a car is used to steer a car sharply along a curve in the road, to steer a car avoiding slip, to steer a car avoiding vibration, to steer a car without losing speed. Okay. So This is a classical conceptual question on this Ackermann steering. So when a car turns, inner wheel goes for smaller radius, right? And outer wheel goes for larger radius. So they must rotate about the same instantaneous center. Okay. The problem with Ackermann is if both wheels turn at same angle, their velocity directions don't meet at one point. No common ICR, and then the wheel slips sideways. Okay. So Ackermann's steering condition we have already seen. It is cot phi I minus cot phi naught is equal to d by L, or phi O I should say rather. So this is the inner wheel angle and this is the outer wheel angle. Okay, so it ensures that all wheels interact at the same ICR and there is no slip. Okay, so the option to steer a car avoiding slip is correct because this is the main purpose. It ensures pure rolling condition. The other option that we have is to steer a car sharply along a curve on the road. This is false because turning sharpness depends on steering angle, magnitude and geometry. Ackermann does not make turning sharper. It only ensures correct geometry, which is no slip. Okay. The third option is to steer a car avoiding vibration. This is also false. Vibration is related to suspension and the road conditions, not related to Ackermann steering. And the fourth option here is to steer a car without losing speed. This is also false. Why? Because speed loss depends on friction or engine power. Ackermann does not control speed. So, different angles are there for inner and outer wheels. For that, because of that, we get common instantaneous center of rotation to avoid the slip. Okay, so Ackermann steerings make all wheels agree on one turning center, so no wheel has to slip. Okay, I hope this question is clear. Let's move to the next question. A wheeled mobile robot made with 3 omnidirectional wheels has 2 degrees of freedom, has 3 degrees of freedom, can be controlled by the rotation of the barrels, can move without slip on a flat surface. Okay, so this basically checks your understanding of omni wheel kinematics versus conventional wheels, right? So for a robot moving in a plane, the full motion is xy psi. Xy is translation and let's say psi is our rotation. Okay, so there are total 3 degrees of freedom. So in conventional car-like robots, there are 2 degrees of freedom due to constraints, whereas in omni-wheel robot, there are 3 degrees of freedom and it is fully controllable. So why do omni-wheels give 3 degrees of freedom? Because every omni-wheel has roller. We saw the mechanism wheel. So it allows motion perpendicular to the wheel direction as well. So there is no non-holonomic constraint. The robot can move forward, sideways or can rotate. Okay, the other option is it has 3 degrees of freedom, which is true. Okay, because it can control x dot, y dot and psi dot, all of them. It is fully controllable. The first option is it has 2 degrees of freedom. No, that is true for conventional wheels, and omni wheels remove that limitation. Option 3 is can be controlled by rotation of the barrels. False. Barrels or rollers are passive and they are not actuated. So control is through main wheel rotation and not the rollers. And the other option is it can move without slip on a flat surface. It is false because omni wheels intentionally allow sliding. Okay, that's how sideways motion happens. So there is slip through rollers, but it is controlled slip. Okay. So you have to remember that for omni wheels it is 3 degrees of freedom and there is no steering needed. Rollers are passive and the sliding is allowed but not pure rolling. So omni wheels trade slip for freedom. They Allow sliding to achieve full motion. All right. Let's move to question 7. A practical wheeled mobile robot on a flat surface can move with zero slip, can move only with non-zero wheel slip, must generate tractive forces by deformation of the wheel on the ground or the ground, must generate tractive forces by rotation of the wheel. So far, we have studied V is equal to R omega, ideal rolling condition, and slip lambda is equal to 0. But in real systems, this is not physical achievable. Why? Because motion requires tractive forces. Tractive forces come from friction and deformation. We saw this. So either wheel or the ground must deform to generate these tractive forces. Okay. The crucial idea here is if slip is 0, exactly, there won't be relative motion at contact. There won't be any shear deformation. There won't be any traction force being generated. So wheel cannot move forward in that case. Okay. So the second option that we have here is it can move only with non-zero wheel slip. It is true because a small slip is necessary. This creates shear deformation and traction. Without slip, there is no motion. Okay. The third option is that it must generate tractive forces by the deformation of the wheel or the ground. This is true because deformation happens at the contact point, and contact point, this contact patch is there. It's not a point generally. It creates a friction force, and friction force helps in motion. It's also correct. The first option is that it can move with zero slip. This is false because it is used in theory, it is an ideal assumption, but it is not possible in practice. Real motion always needs small slip. Okay, the fourth option is it must generate tractive forces by rotation of the wheel. This is also false. Rotation alone does nothing. Without friction, wheel spins in place. So motion must come from the ground and motion comes from the ground and rotation. Just hold on. Yeah, and from motion comes from the ground reaction and not from the rotation. So this is also wrong. So ideal rolling is lambda is equal to 0. Small slip is necessary. Deformation is required, but and also traction drives the motion. That is all you should know. So a real wheel moves because it slightly slips and deforms, not because it perfectly rolls. All right. Okay.
Hello,
Sorry.
hello, ma'am.
Yeah, please.
Ma'am, I am currently pursuing the mechanical engineering in BTech.
Hmm.
Ma'am, in our class, robotics have not there, but in this chapter, it have too many advanced.
Hmm.
Actually, I can't understand the advanced one cause of I don't have any introduction of robotics.
Okay.
So can you suggest me what should I do?
So there are many NPTEL courses available for
No,
introduction to
ma'am.
robotics.
No, ma'am. I didn't choose this. Our college has done it.
Okay. So your
Actually, ma'am, we have a introduction of robotics, but our faculty
yeah.
did advanced parts.
Okay. So no, without introduction to robotics, I think it is difficult to understand these.
Yes,
So
ma'am. Actually, our faculty has done wrong, but we are suffering from this.
so are you
What should I do, ma'am?
so you have been asked to take this course on a mandatory basis and then you're supposed to appear for exam as well, right?
Yes, ma'am.
So you
Actually, we have done two NPTEL in previous IoT. I have done and also hydraulic fuels.
okay.
But this one is too complicated for us, ma'am.
So
For me,
what I would suggest
actually.
is there are NPTEL courses available for introduction to robotics. Don't wait for getting a certificate from there, or doing whatever is required, and then you get a certificate of whatever it is. Instead, go and watch the lectures. Here also, I think everything has been covered, but yeah, it is a bit of advanced course and it is not right from the scratch. So you should go immediately to introduction to robotics course, watch all
Acha.
the lectures there, solve the assignments, so that
But
this.
ma'am, but ma'am, time is too short. No,
Okay, because when do you have exams?
18 April.
We really have less time. So aren't you able to understand the lectures?
Ma'am,
But
little bit, not too clear.
okay, so what I would suggest is the following. See, in this lecture, uh, can you wait for some time so that we finish this this question answer part, and then I can answer your question?
Yes,
So,
ma'am.
yeah,
No problem.
in general, I would just say that you know what are the topics here, right? For example, it starts with DH parameters, it starts with manipulators. You start right from the kinematics and dynamics of manipulators. You start from basics, but then this course does not focus on lot on basics, and it moves forward very fast to advanced concepts on building on top of all of these concepts that I'm talking. So when this course
Okay.
does that, what you can do is, जो नहीं समझ में आ रहा है, let's say you started with DH parameter, you felt that the pace was too fast, I haven't understood the things properly, and it has become too tough for me in just 1 hour of lecture. That might be happening for sure.
Hmm.
Yeah,
Yes, ma'am.
yeah. So go and read
How the
the.
formulas, ma'am? How the formula are putting to?
So what you are supposed to do is, don't watch everything since you are running low on time. Go and watch this specific topics. अगर DH parameter उठाया, you have hundreds of lectures available on YouTube. Go and read from there. The next thing is, let's say, kinematics of serial manipulators. You have a lot of lectures available. Go and see all of them, because or you just refer to the NPTEL lecture on introduction to robotics, where this part is being taught. So you have to go through the content of this lecture. You go to other lecture from where you can see that, okay, now I can understand the things in detail. Once you get a grasp of all of these things, come back here, listen the lecture at 2x speed, you'll be able to understand.
Okay, ma'am.
That is the best I can suggest for you given the time that is left. You should have come to me earlier. You're coming at a very later point of time. It's April. The course started in January, I believe.
Actually, ma'am, I had seen in YouTube of your video
Okay.
something I am understand, something I am not.
Okay. But
Actually, my
that is why
phone
you
is
need to attend
yes, ma'am.
these lectures. That is why you need to attend these lectures in person, so that you can ask your doubts and clarify everything. If you rely on recording, it would be a problem, I think. Okay, that's fine. Since you are short
I
of
am
time.
seeing your videos week one, week two, week three. What have you done in also see dates?
Yeah, I would suggest what you have to do. Don't go for the lectures directly. If there is a, let's say, a topic on dynamics of serial robots, look for it in ITR videos, or if some other material is available. As of now, I can only remember NPTEL. But if there is any, go and see that video. You'll understand everything there in detail. Once you understand there, come back here, you'll be able to understand everything. That is the best suggestion I can give you. And then for problem solving, you when you see my videos, it would be like, हाँ problem कैसे solve करना है, because you might have submitted assignment questions also, right? How are you
Yes,
doing that?
ma'am.
Because all of these things, whatever I'm teaching, helps you in assignment.
Yes, ma'am.
So I think, and the questions would be similar, I guess so, in your exam as well, though I'm not aware. But what I'm saying is, read it from some other source, maybe
Ma'am, can
introduction.
you tell me how the IST question makes? It is tough or মানে it is tough or simple as
I'm not
previous I did.
aware. I'm not aware. I'm not aware at all. If you have this doubt, you can do one thing. You post it on this. What do we say? You have a Google group, right?
Hmm.
Associated with your NPTEL account.
Hmm.
So
Yes, ma'am.
when you log in, then you get Google Forum wala link. You go there and you post. So the people who are engaged in all of this process would be telling you the answer, because I'm not engaged. I'm only supposed to teach you, tutor you, and I have no hands in how NPTEL does the thing. So I'm not aware of it exactly. It would be nice if you post there so that NPTEL can themselves answer you the question. Okay?
Okay, ma'am.
Okay. Let's move forward. So in this question, I don't know why this question looks like this. Let me just check. It's question number 8. Here also it is like this only. Okay. Can move with zero slip is constant, is a function, I think it's talking about slip, is a function of only normal ground reaction, depends on the adhesive coefficient and lies in between zero and product of adhesion coefficient and normal reaction. So the question is about tractive forces limits and friction modeling. Okay. So the tractive force which we saw some time back at the wheel ground contact force is mu a, which is a function of lambda into n. And this term is the adhesion coefficient, and this is the normal reaction. So from theory, we know that this force should lie in between mu a into normal and should be greater than 0. This means the minimum that you can have is 0 and maximum is this. So physical meaning is, if Ft is equal to 0, there is no motion. If Ft is equal to this side quantity, it is maximum traction. Beyond this, slip becomes unstable. So the question here is, so let's look at the option. It lies in between 0 and the product of adhesion coefficient and normal reaction. This is true. This exactly matches the friction limit. It comes from Coulomb friction model, right? So this is true. The first option here is it is constant. It is false, because Ft depends on lambda and surface condition. So it is not constant definitely. In option 2, we have it is a function of only normal ground reaction force. It also depends on adhesion coefficient mu a, which is not taken care of here. And mu a depends on slip. So it is false. And third option is it depends on only the adhesion coefficient. This is also false, because missing normal force n and both of them are required definitely. So this is also incorrect. Okay. So whenever you see this tractive force, you have to know that the tractive force has to be less than mu into normal. It depends on slip and it is a bounded quantity. Traction is limited. The ground can only push so much before slipping. Okay. So you cannot assume infinite traction coming up from there. Okay. Let's move to the next question. The main kinematic difference between the wheeled mobile robot and fixed base serial manipulator is, wheeled ground contact points gives rise to non-holonomic constraints which reduces the degrees of freedom. Wheeled ground contact point gives rise to non-holonomic constraints which reduce the space of velocities. The moving base makes the wheel mobile robot impossible to control accurately, and the moving base leads to a smaller workspace of the robot which it is carrying. Okay, so let's start from fundamentals. Let's say we have fixed base manipulator. Okay, where robot is there, it is fixed, and then there is a manipulator. So these joints impose holonomic constraints. These constraints are on positions. You cannot have link going anywhere, right? For example, Fq is equal to 0. It reduces the configuration space. Okay, but in wheeled mobile robots, the wheel and the ground contact introduces non-holonomic constraints. Example, x dot sine phi that we saw minus y dot cos phi is equal to 0. We have done a complete derivation today. So for manipulator, the constraint type is holonomic. It reduces configuration degree of freedom. But for wheel mobile robots, it's non-holonomic and it just reduces the velocity space. Okay. So there is a very important statement that non-holonomic constraints do not restrict configuration space but restrict the space of velocities. Okay. So I think we had an option reduces the space of velocities is the correct option. The first option is it reduces the degrees of freedom. It is false because degrees of freedom in configuration space remain same. Only velocity degree of freedom is reduced. So this is trap. The third option is moving base makes it impossible to control accurately. This is also false. WMRs are controllable, just they are more complex and they're not, it is not impossible. So this is wrong. Option 4 says the moving base leads to a smaller workspace of the robot which it is carrying. Opposite is true. Moving base means larger workspace, right? Because you can move apart from manipulating. So if there is non-holonomic constraint coming into picture, you need to think immediately that it does not reduce configuration degrees of freedom. It just reduces velocity possibilities. It cannot integrate to position constraint. So a WMR can reach anywhere but cannot move in every direction instantly. Okay. I hope this is clear. Let's move to the next question. A wheeled mobile robot on a generic uneven terrain can move without wheel slip, cannot move without wheel slip if the axle length is fixed, can move without wheel slip only if the axle length is variable, can move without wheel slip if the wheel can tilt and distance between the point of contact with ground can change. Now, on an uneven terrain, the key issue is contact. So if let's say your terrain is like this, okay, so your contact points of wheel are not at the same level. So two wheels are connected by a rigid axle, right? And contacts point, let's say there are two contacts point P and Q. So axle length would not be equal to what is the actual distance because of this not same level thing. So there is a geometry mismatch and it is impossible to satisfy. So there is rigid axle constraint. Also there is no slip constraint. Okay. Therefore slip becomes unavoidable because this you have to follow anyway. So this becomes unavoidable. So the option is, so let's see the second option. It cannot move without a wheel slip if the axle length is fixed. True, right? Because fixed axle means fixed distance between wheels. Terrain is changing contact distance. So slip must occur. Option 3 is it cannot move, sorry, it can move without wheel slip only if the axle length is variable. That's true. Because one of them only will be able to change. This is the advanced solution. Example, if there are torus shaped wheels or there are passive joints as discussed in the lecture, it allows geometry to adapt. Okay. Let's talk about the first option. It can move without wheel slip. On uneven terrain, geometry mismatch exists. Slip is unavoidable. Only possible with special mechanisms. So this is false. Okay. And the last option is can move without wheel slip if the wheel can tilt and the distance between the point of contact with ground can change. I think we saw this, right? Oh yeah, this is true for torus wheels and passive joints. I think I mixed two options. The third option was can move without wheel slip only if the axle length is variable. Yeah, that's true. So this is the correct option. B, C and D. So uneven terrain breaks rigid geometry unless the robot adapts. Slip is unavoidable. Okay. Let's move to the 11th question. The contact equations between two surfaces in single point contact are only for smooth and at least twice differentiable surfaces. Model the 5 possible degrees of freedom between the two contacting surfaces are in terms of the metric curvature and torsion from the two surfaces are in terms of the derivatives of the variables describing the contact. We are studying contact between two surfaces at a single point. So every surface can be described as function of u and v. So what are these? Okay, x, y, z is a function of u and v. That so contact is described by u1, v1, u2, v2 and psi. So there are total 5 degrees of freedom for contact. 2 from surface 1, u1 and v1, 2 from surface 2, u2 and v2 and 1 from rotation, which is psi. So they relate u1 dot, v1 dot, u2 dot, v2 dot and psi dot. They relate to velocities which are vx, vy, omega x, omega y and omega z. So they are velocity equations. Okay. So to define the tangent vectors, it is fu and fv. For curvature, it would be second derivative, and for torsion, it would be even higher derivative. So surface must be smooth and at least twice differentiable. Okay, you can use distance scaling. For curvature, you can use bending, and for torsion, you can use twisting. So the first option is only for smooth and at least twice differentiable surfaces. True, because you need derivatives. First tangent and second curvature. Second is model the 5 possible degrees of freedom. True, contact has 5 degrees of freedom. Equations describe their evolution. Third option is in terms of metrics, curvature and torsion form of the two surfaces. True, because these define geometry of surfaces used directly in equations. And option 4 is it is in terms, so all of these are in terms of derivatives of the variables describing the contact. True, because equations are u dot, v dot and psi dot, so they are differential equation. So when you see contact equation, you should know that they are differential. They require smooth surfaces, use geometry, metric, curvature and torsion, and they are 5 degrees. They have 5 degrees. This contact point has 5 degrees of freedom. So contact motion is governed by how surfaces bend and twist, captured to derivatives. Okay. Okay, let's move to the next question. So as discussed in the lecture, a planar 3R serial manipulator is redundant if only the xy position of the end effector is considered. Is redundant if the position and orientation of the end effector is considered. Is redundant since the Jacobian matrix is not square. Is never redundant. So we have a planar 3R manipulator. We have 3 joints, right? Theta 1, theta 2 and theta 3. So degrees of freedom that we have here is 3. What is redundancy? A robot is redundant if the degrees of freedom is more than the task dimension. So if let's say we take a case of only position, which is xy, okay, so they are just 2 variables, but the robot has 3 joints, so 3 is greater than 2, right? The number of joints are greater than 2, degrees of freedom are greater than task dimension, so your robot is redundant. So infinite solutions exist. Extra degrees of freedom can be used for obstacle avoidance or optimization, all of these. The second case can be you have position as well as orientation, x, y and phi. There are 3 variables. This means that you have 3 degrees of freedom. So sorry, the robot has 3 degrees of freedom and your task requires 3 dimensions. So you have 3 equal to 3 and this is not redundant. Okay. So your question has, it is redundant only if xy position of the end effector is considered. True, because degrees of freedom here is 3 and task is just 2. So extra degree of freedom leads to redundancy. Second option is redundant if position and orientation are considered. No, it would be degrees of freedom is 3 and task is also 3. So it is not redundant. Exactly constrained. Okay. Third option is, it is redundant since the Jacobian matrix is not square. Jacobian size depends on task. For xy, when we are considering, the Jacobian is 2 cross 3, and when x y and phi are there, it is 3 cross 3, which is square matrix. So redundancy is about degrees of freedom versus task and not matrix shape alone. Okay. And the other option is it is never redundant. No, redundant for position only tasks. Okay. So whenever you see redundant manipulator, it's degrees of freedom versus task dimension. If so, I'm writing, if degrees of freedom is greater than task, it is redundant. Okay. If degrees of freedom is equal to task, it is non-redundant. If degrees of freedom is less than task dimension, it is underactuated. Redundancy means extra joints beyond what the task demands. Okay. Let's move to the 13th question. In the kinematic model of the human arm discussed in the lecture, only 4 joint rotations are considered, as considering all the joints will make the model too complicated. Only 4 joints are considered as the motion of the hand is constrained to be in a plane. Only 4 joints are considered as the motion of the hand is in 3D space. Only 4 joints are considered since 4 joints are enough to make the system redundant. Okay. So the human arm, this we have already seen. It has, shoulder has 3 degrees of freedom. Elbow has 1 degree of freedom. Wrist has 2 to 3 degrees of freedom. So in total we have 7 degrees of freedom. We simplify the system. We assume that motion of the hand is restricted to a plane in 2D motion. Okay. So what does planar motion means? It means that you just have x, y and phi, 2 positions and 1 orientation. Total degrees of freedom that you have is 3 DOF. Now we choose degree of freedom is equal to 4. So 4 is greater than 3, which means it is an example of redundant systems. So this is for enough flexibility and it is still simple to model. Okay. So the first option is only 4 joint rotations are considered, as considering all the joints will make the model too complicated. True, because motion is restricted to 2D. So fewer joints are needed. 4 joints give sufficient control and redundancy. So this is correct. Sorry. I think plain wala. Yeah, this is correct. The first option that we have is only 4 joints are considered because full model is complicated, because while simplification is true, this is not the reason what we have studied. The real reason is the planar constraint, so it is wrong. The fourth option, I think, okay, only 4 joints are considered as a motion in 3D space. If motion were 3D, we would need more degrees of freedom greater than 6. 4 DOF is not sufficient for full 3D, so it is also wrong. And then only 4 joints are considered since 4 joints are enough to make system redundant. Redundancy is a consequence and not the reason. So primary reason is planar motion constraint. Okay, so this is also incorrect. So human arm simplified model has reduced degree of freedom. It assumes planar motion and it keeps slight redundancy. We reduce the human arm to 4 joints because we force the motion to stay in a plane. Okay. Let's move to 14th question. The kinematics of a 3-wheeled mobile robot discussed in the lecture has 3 independent actuations, 2 in the rear wheel and 1 in the front wheel, has passive tilting at the 2 rear wheels, has passive rotation of the front steering wheel, has non-holonomic pure rolling constraints at the 3 wheels. So the structure of the robot is it has front wheel, okay, which is steering actuated, and rotation, which is passive. Right. So, and in rear wheels, what do we have? They are driven, actuated rotation, and then there is passive tilting in advanced model. So the first option is it has three independent actuations, two in the rear wheel and one in the front wheel. This is true because rear left wheel has one actuator, rear right wheel has one actuator, and front steering has one actuator. So in total we have three actuators. Okay. Second option is has passive tilting at the two rear wheels. This is also true because in uneven terrain model, rear wheels can tilt. This helps maintain contact and reduces the slip. The third option is it has passive rotation in the of the front steering wheel. This is true because steering is controlled but rolling rotation is not independently actuated. It rotates due to motion. Okay. And the fourth option is has non-holonomic pure rolling constraints at all the three wheels. Each wheel enforces no lateral velocity, so three wheels imply three non-holonomic constraints. So this is also true. So the system has actuated degrees of freedom, it has passive degrees of freedom, and it also has non-holonomic constraints. That is why modeling is complex. So if you see three-wheeled robot or a tricycle, you can understand that it is three actuators, two drive and one steer, and then passive wheel rotations are there and non-holonomic constraints are there. The robot is driven by three actuators, but its motion is heavily restricted by the rolling constraints. Okay. Let's move to the next question. The stability of a wheeled mobile robot moving on uneven terrain depends on the speed of the robot, depends only on the unevenness of the terrain, depends on the height of the center of mass from the surface at the instant, depends on the net resultant force acting at the center of mass. So when a robot moves on an uneven terrain, stability depends on where it tips over or it stays balanced. Okay. So the key idea here is if the line of action of net force is relative to the support polygon falls outside the support polygon, the robot trips. Okay. So net force at center of mass of a mobile robot on, let's say, an uneven terrain. Here gravity acting here is mg. There could be some inertial forces due to motion, and then there are contact forces here. These combine into net resultant force at center of mass. Now, if the resultant force lies outside or the resultant force actually is more uh, what would I say? If it falls such that it moves beyond the support polygon, the robot tips. So the correct option is it depends on the net resultant force acting at the center of mass. This includes gravity, acceleration effects, fully determines the stability of the robot. The other option is depends only on speed. No, because speed alone does not determine stability. Direction and acceleration matters. Okay. And second option is depends on unevenness of the terrain. No, terrain affects the stability, but is not the only factor. And the third option is depends on the height of center of mass. This is false because height affects the stability, but it is not sufficient alone. So this is also wrong. Okay. So when we talk about stability of the mobile robot, we must remember that we are talking about center of mass, we are talking about forces acting on the center of mass, and we are talking about the support polygon. So a robot is stable only if the net force through its center of mass keeps its balance over its support. Okay, not outside the support. Okay. Now let's move to the next question. The contact equations discussed in the lecture for pure rolling are similar to the constraint equations for rotary joint, are similar to the constraint equations for a spherical joint, are different from the constraint equations for a spherical joint since the equations are in terms of derivatives, are different from the constraint equations for a spherical joint since the degrees of freedom at the contact are different. So that's, we are comparing classical joints. Okay, like spherical joint is an example, and we are comparing contact equations, which is pure rolling. Okay, so if we talk about spherical joint which is ball joint, So in this case, we have constraint where x1 is equal to x2, y1 is equal to y2, and z1 is equal to z2. So these are position constraints. These are algebraic equations. So they are holonomic constraints. Okay. Now, in contact equations, when we talk about these contact equations in pure rolling, they relate as u1 dot, v1 dot, u2 dot, v2 dot, and psi dot. These are velocity constraints. They are differential equations and not algebraic equations, and they are non-holonomic. Okay. So the key difference here is when you talk about spherical joint, it's holonomic. In rolling case, it is non-holonomic. Equation form here in spherical joint is relates to position. In rolling, it relates to the velocity and derivatives. In general, the nature of equation in spherical joint is algebraic, whereas in rolling or contact equation, it is differential. Okay. So are similar to the constraint equations for the rotary joint is false. Why? Because rotary joint is holonomic and contact equation is non-holonomic. Second option is it is similar to that of spherical joint. This is also wrong because spherical joint has position constraints and contact has velocity constraints. Okay. Third option is different since the equations are in terms of derivatives. This is correct because contact equations depend on time derivatives. Spherical joint depends on positions. So there is a fundamental difference. And the fourth option is different because degrees of freedom are different. This is false. Why degrees of freedom differ? That is not the key reason emphasized. So the main reason is derivative based equation. So this is wrong. So for contact equations, you have to understand that there are velocity constraints. These are differential equations and they are non-holonomic constraints. Whenever you see joint constraints, you have to understand they are position constraints, algebraic equations, and they are holonomic. All right. So joint constrains the position, but rolling contact constrains the velocities. That is the key idea. Okay. Let's move to the next question. 17th. For the three-wheeled mobile robot with torus-shaped wheel and moving on uneven terrain, the trace of the wheel center and the ground contact point is the same. The wheel tilts as it rolls. The wheel slip is negligible since the wheel mobile robot is moving very slowly. The wheel slip is negligible since the distance between the point of contact with the ground is adjusting so as to have instantaneous center. Okay. So a special design is introduced to handle uneven terrains. Torus-shaped wheel plus passive joints. So the goal is to avoid slip on uneven terrain. The problem with normal wheels is what? It has fixed axle. It has, if there is uneven terrain, the contact points mismatch, and then there is no common instantaneous center of rotation and slip occurs, right? Solution is torus-shaped wheels and passive tilting that we saw here. Okay. This allows wheel orientation to change, contact geometry to adapt, and ICR to exist. Okay. Now, from the lecture, what we have seen from simulation and analysis done there, we have seen that wheel tilts while rolling. Contact points move differently than the wheel center, right? And geometry adapts continuously. So the correct option here is the wheel tilts as it rolls because passive joints allow tilting. It helps maintain the proper contact. Okay. This is clearly shown in the simulation results. The other option that we have is the fourth option. The wheel slip is negligible since the distance between the point of contact with the ground is adjusting so as to have instantaneous center. True. Adaptive geometry. Okay. So consistent from this we get consistent ICR, though it is changing. Okay. There is no mismatch. There is no slip. This is the whole purpose of this design. So this is also correct. The first option is trace of wheel center and ground contact point is the same. False. On uneven terrain, so contact point moves differently. Wheel center follows different path. So clearly shown in lecture. So this is wrong. And the third option is wheel slip is negligible since robot moves slowly. This is also false. Slip is not about speed. Okay. It's about geometry and compatibility. Right. So even slow motion can slip if geometry is mismatched. So this is also wrong. So when you see torus wheel and uneven terrain, you have to understand that wheel may tilt, geometry adapts, and ICR is maintained, slip is minimized in this way. So the torus wheel adapts its shape and orientation so that the robot can roll without slipping even on uneven terrain. Okay. Let's move to the next question. This is the second last question that we are taking. The dynamics of a three-wheeled mobile robot is similar to a 3 degree of freedom parallel manipulator, is similar to a 3 degree of freedom parallel manipulator with wheel ground contact modeled as a spherical joint, similar to a 3 degree of freedom parallel manipulator with wheel ground contact model with non-holonomic constraints, similar to the three-fingered hand discussed earlier in the course. Okay. Okay, so we are again analyzing tricycle with omni wheels or torus wheels. So think of the robot like this. Each wheel is attached like a kinematic chain. All wheels connect the platform to the ground. So this is like a parallel manipulator, right? Okay, so the degrees of freedom of robot is xy phi. It is xy psi. It is 3 degrees of freedom, so equivalent to 3 of parallel manipulator. In a normal parallel manipulator's constraints are holonomic. It is position based. But in wheel mobile robots, wheel ground contact gives non-holonomic constraints. The system behaves like a parallel manipulator plus non-holonomic constraints. Okay. So, the option that we have is similar to 3 degree of freedom parallel manipulator with wheel ground contact model with non-holonomic constraint is correct because there are three wheels and then there are three chains, platform is a robot body and constraints are from rolling. Okay. The other option that we have is similar to a 3 DOF parallel manipulator. It is incomplete because it does not mention about non-holonomic constraint. Second is wheel ground contact model as spherical joint. This is false because spherical joint is holonomic. Wheel contact is non-holonomic. Therefore, it is completely different. The fourth option is it is similar to three-fingered hand. This is false. The system involves grasping force closure, not same as WMR. So this is also false. So when you see WMR dynamics, you have to understand that it is parallel manipulator analogy. That is something that we have to bring here. And then the constraints are non-holonomic. Okay. So a WMR behaves like a parallel robot whose joints are replaced by rolling constraints. Okay. Okay. With this, we move to the last question. So the stability of a wheeled mobile robot on uneven terrain depends only on the speed of the robot, depends only on the unevenness of the terrain, depends only on the height of the center of mass from the surface at the instant, depends only on the net resultant force acting at the center of mass. Okay. So the core idea here is stability of a robot on uneven terrain is measured by whether the robot tips or stays balanced. So if all the forces acting on the robot combine into a net resultant force at center of mass, which we already saw, which includes gravity, inertial forces and contact reactions. So stability condition is fulfilled if the line of action of the net force lies inside the support polygon, it is stable. If it lies outside, the robot tips. Okay, so it depends on the net resultant force acting at the center of mass. This is true because this captures all the effects together: speed, terrain, geometry. It is complete condition. Okay, the first option is it depends only on speed of the robot. This is false because speed alone is not enough. Direction and acceleration matter. So this is wrong. Second option is it depends on unevenness of the terrain, which is also false. Terrain influences stability, but it is not the only factor, so it is wrong. And third option is depends on height of center of mass. Height affects stability, but again, it is not sufficient alone. So when we talk about stability, we have to think about center of mass, the resultant force, and the support polygon. So a robot stays stable if the combined forces acting on its center of mass keep it balanced over its base. If it tips, it is not. Okay. And with this, we come to the end of the lecture today. If you have any questions, I can take them. else we'll close the session. Is there any question that I need to answer? Okay. So if there are no questions, this was the 11th session, and I think we are just left with one more session, which covers over constraint mechanism and deployable structures, right? So it just has 2 lectures. As far as I can see, it would be not taking much of your time. So kindly go through that. Okay. Watch the lecture properly. Just hold on. I would like to see how much. Okay, it's over constraint mechanism and deployment and kinematic and static analysis. Okay. So there are only 2 lectures that you need to study for the last week. Please do it before you come here. And if you have any doubts for the entire 12 weeks, because your exam is too near, it's on 16th April, as I know now, please read it, and then we'll meet for the last session on next Monday. Okay. So keep preparing well for your exams. Okay. Watch all the lectures, watch all the tutorial sessions, ask any doubt that you have in the discussion forum, and we'll meet next Monday at the same time, 6 p.m. to 8 p.m. Thank you so much. See you next time.